Good evening to all of you all. We wish to study the effect of combining two or more prisms. So first let us consider a single prism. We have a prism here of refractive index mu. The refracting angle of the prism is A. The incident angle on the first surface is I1. The ray travels from rarer medium to a denser medium, so it bends towards the normal. N1 is the normal. Then it falls on the second refracting surface. The angle of incidence there is R2. Now it is going from a denser to a rarer medium, so it bends away from the normal. And the angle of emergence is I2. The normal is N2. Now we wish to know what is the deviation. The ray would have gone straight along this dotted line, but now it has got deviated by a certain angle delta. We wish to know what is delta in terms of I1, R1, R2 and I2. Well, if I call this as O dash, if you see triangle BCO dash, this delta is an external angle. That external angle is equal to the sum of the two internal opposite angles. The internal angles are, if you see this cross which I marked here, is I1 minus R1, and the circle that I have put here is I2 minus R2. I2 minus R2 would be this circle. Therefore, I can say delta is I1 minus R1 plus I2 minus R2. Or I can say it is I1 plus I2 minus R1 plus R2. Now, if you consider the quadrilateral, ABOC, it is a cyclic quadrilateral because BO is normal, CO is also normal, so the opposite angles are 180. So therefore I can say angle A plus angle O is 180. Now if I consider triangle BOC, in triangle BOC I can say angle R1 plus angle R2 plus angle O is also 180 degrees. Yes. So from comparing these two, yes, if you equate these two, O cancels and you get R1 plus R2, angle R1 plus angle R2 equal to angle A. So therefore the deviation becomes I1 plus I2 minus A. I1 plus I2 minus A. That would be the deviation. I1 plus I2 minus A. Now, if you apply Snell's law to the first surface, I can say 1 sine I1 is equal to mu sine R1. If I1 is small, the angle of incidence is small, the angle of refraction will also be small, and we can approximate I1, sin I1 as I1, so I1 will be mu R1. Similarly, for the second surface, we can say I2 will be mu R2. So if you substitute it there, you get delta is equal to mu R1 plus mu R2 minus A. So that would be mu into R1 plus R2 minus A. R1 plus R2 is A. So I'll get mu A minus A, or A into mu minus 1. So this is the approximate deviation when the angle of incidence is small. The angle of the prism is also assumed to be small. A is also assumed to be small. So the deviation will be a small value in case of small angle prisms. Now, this deviation is a function of mu. Now, mu does not depend only on the material of the prism. It also depends on the color of the light which we are using. Well, it is seen that mu depends on the wavelength lambda of the light in vacuum. So now we know lambda for violet is 400 nanometers approximately, and for red it is 700 nanometers. Now there is a relation known as the Cauchy's relation, which gives mu as A plus B by lambda squared, where lambda is the wavelength of the light falling on the material, and A and B depends on the material of the prism. So from this it is very clear, since the wavelength of violet is less compared to wavelength of red, so we can say mu of violet will be greater than mu of red. So therefore, if I use this formula, I can say the deviation of violet will be greater than the deviation of red. So now if you have the prism and there is say white light, if there is white light, that white light will disperse. Why does it disperse? Because the deviation of each of the colors is not the same. The deviation of violet is the maximum and the deviation of red is the minimum. So you have the white light splitting this way into the constituent colors. The central one we can call it as yellow. So we can now talk about the angular dispersion. The angular dispersion is given by the spread of the spectrum, that is nothing but dV minus dr. That will be the width of the angular width of the spectrum, the deviation of the violet minus the deviation of red as measured from the incident angle, as measured from the incident ray. So this will be delta V, this will be delta R, and for yellow it will be delta Y. So we say the angular dispersion is del V minus del R, and you can write del V as A into mu V minus 1 by using this formula. Delta is equal to A into mu minus 1 minus A into mu R minus 1. So this will result in A into mu V minus mu R. That is the angular dispersion. The mean deviation, because the deviations are different, we talk about the mean deviation. The mean deviation is generally taken for the yellow ray. The mean deviation is given by del Y, which is nothing but A into mu Y minus 1. Now we define a quantity known as the dispersive power of the prism. Dispersive power of the prism. It is given by the symbol omega, and it is the angular dispersion divided by the mean deviation. That is del V minus del R by del Y. That is the dispersive power of the prism. Now we can write this as, we can also write this as, therefore we can also write dV minus dr as omega into dy, or dv minus dr is nothing but a into mu v minus mu r, that is equal to omega into a into mu y minus 1. Yes, so a cancels. You can also write omega as mu v minus mu r by mu y minus 1. This is another way of writing omega in terms of the refractive indices for violet, red and yellow. Now, based on this, let us see combination of prisms. Supposing we have one prism like that and another prism like this, and let us say there is white light falling on the first prism. The parameters are mu, the mean refractive index. This is for yellow. This is for yellow, is mu. For the angle of the prism is A. The dispersive power is omega. For this it is A dash, and dispersive power is omega dash, and refractive index is mu dash. Refractive index is mu dash. That is again for the yellow light. So when you have white light here, what is going to happen is it will disperse. That dispersed thing is going to fall on the other prism, but because it is inverted, the deviation is going to be in the opposite direction. So let us see what is the net angular dispersion. The net angular dispersion is del V minus del R for the first one, that is in the clockwise direction, and since this is the anti-clockwise direction, we will say it is del V dash minus, we will say minus because it is in the other sense. This was in the clockwise sense, this is in the anti-clockwise sense. However, the prisms are both the apexes are pointing upwards, then it would be plus here, plus it would be dv minus dr plus dv dash minus. But since we have got an inverted prism, we are putting a minus because the deviation will be in the opposite sense. This is the net angular dispersion, and we can now write this as, we know dv minus dr is omega del y minus omega dash del y dash. Yes, that is the net angular dispersion. What is the net mean deviation? The net mean deviation is nothing but del y minus del y dash. Now we can have two situations. There are two conditions for the combination of these two lenses. We can have dispersion without deviation and deviation without dispersion. Let us try to understand this. Yes, let us try to. So the deviation is not there, deviation is 0 and dispersion is there. So if deviation is 0, we can say del y minus del y dash is equal to 0, which implies del y is equal to del y dash. So what will be the net angular? The net deviation is 0. So what is the net angular dispersion? The net angular dispersion can now be written as omega del y minus omega dash del y dash. Omega dash del y dash is equal to del y. So this is equal to del y, or you can say omega minus omega dash into del y. That will be the net angular dispersion. Yes, where we can say del y is a into mu y minus 1, and of course del y dash is nothing but a into mu y dash minus 1. Both these will be equal since del y and del y dash are equal. These two are equal. Now the other condition that we can get is net angular dispersion is 0. So this quantity is 0. So we will have omega del y is equal to omega dash del y dash. If this quantity is 0, you will have this. So what will be the net deviation now? We know the net deviation is del y minus del y dash. We can substitute for del y dash. Del y dash should be omega del y by omega dash, or this will give us del y into 1 minus omega by omega dash. That would be the net deviation, where del y again can be put as a into mu y minus 1. Del y will be a into mu y minus 1. What we must understand is diagrammatically what this means. Let's try to understand this diagrammatically with a ray diagram what this looks like. If you have a prism like that and another prism like that, you have white light falling. We are saying net deviation is 0, but there is dispersion. So since net deviation is 0, you have basically this is white light. You have basically the yellow light coming parallel to the incident white light. That is why the net deviation is 0. And there will be a slight spread of red here and violet here. So the net angular dispersion is not 0. Whereas in the second case, if you had a prism like that, white light comes out, white light goes in and white light comes out. But there is a net deviation which is taking place. The net deviation is not 0. These two are not parallel. Well, you might ask, can the net deviation and the angular dispersion both be 0? Well, if both are 0, see what happens. The net deviation is given by dy minus dy dash. If this is 0, and also the net dispersion is omega dy minus omega dash dy dash. If this is also 0, well, if del y is equal to del y dash, if you substitute here, you will get omega equal to omega dash. It means the two prisms are having the same dispersive power. Their angle, their refracting angles can be different. Their refractive index for the yellow light can be different, but the dispersive powers are the same. If the dispersive powers are the same, well, you will have a situation whereby there is a light, white light enters here and white light comes out parallel. Yes, this omega and omega dash are equal. You would find the emergent light also white and parallel to the incident light. Thank you.